The Pratt Whitney TALON X low-emissions combustor revolutionary results with evolutionary technology by Randal G. McKinney, Domingo Sepulveda, William Sowa, and Albert K. Cheung from Pratt Whitney, East Hartford. Pratt Whitney has developed a family of reduced NOx combustors for aircraft gas turbine engines using the rich, quench, lean approach. This paper describes an extension of this family to an advanced concept called TALON X that has demonstrated the potential for very low NOx levels in development testing. The requirements for a combustor design are described and the key technologies investigated, including a uniform rich primary zone, optimized quench, advanced cooling, and residence time reduction are discussed. Results demonstrating the potential of TALON X to produce NOx levels 70% below CAP2 levels are presented. Over the past decade, Pratt Whitney has developed the TALON family of low NOx combustors for commercial aircraft gas turbine engines. Each combustor in this family has achieved progressively lower levels of NOx while still employing the proven, simple, and safe rich quench lean combustor design approach. Rich quench lean can be shortened to RQL. Pratt Whitney is committed to provide its customers with robust, highly maintainable, low-cost combustor components that provide significant margin to emissions requirements over the lifetime of the product. To this end, the RQL design has been fully evaluated for its potential to meet customer and community needs for low emissions in near-term and long-term, which is beyond 2015 products. The newest member of this family, TALON X, has produced NOx levels which improve upon current TALON 2 by 25% in rig and engine tests of early prototype concepts, indicating the potential to achieve NOx levels up to 70% below CAP2 regulations in a future product. Additional product concerns of safety, fuel burn, or CO2 emissions reduction targets. Operability or reliability and customer economics are also well addressed using TALON X. Let us see the combustion system requirements and design process. The inviolate requirement for aircraft system level safety, along with the need for gaseous, smoke, CO2, and community noise reductions combined with airline economics requirements can impose competing constraints on combustor design. The interrelationships between these requirements, including emissions, pressure loss, stability, operability, altitude relight, exit temperature quality, cost, and weight are a key part of the evaluations that were done to understand the viability and desirability of RQL for future applications. The iterative nature of the commercial combustion system design process can impede the satisfaction of emissions targets as these constraints are addressed in the design. These impediments were considered for TALON X, with favorable results in the final evaluation as it relates to product readiness. Now let us explore the combustor design strategies. In the pursuit of reduced combustor emissions, a number of combustor design strategies are being pursued, including the traditional RQL approach employed in the TALON family and the lean staged or the lean direct injection concept. The RQL approach has been in use for many years in gas turbine combustors. It is a reliable, low-cost approach with many advantages in meeting the full range of combustion system requirements, including the NOx emissions targets. Staged combustor designs, such as the axially staged combustor, offer additional flexibility to reduce NOx emissions by accommodating lean operation at selected engine power levels. These lean staged systems have the disadvantage of increased cost, weight, and complexity, along with the potential for combustion instabilities and higher emissions of carbon monoxide and unburned hydrocarbons due to quenching. Moreover, the introduction of these systems often requires consideration of multiple system-level impacts on hardware and control software. Pratt Whitney has partnered with NASA in several programs, such as HSR, AST, and UET, to investigate advanced combustor designs as illustrated in Figure 1. These programs established the feasibility of NOx reduction technologies and helped guide the development of NOx stringency regulations. The HSR program established best-to-date RQL performance levels in idealized rig testing that approached lean, pre-mixed, pre-vaporized NOx emissions. However, this potential needed to be translated into viable product designs. The AST program provided the opportunity to investigate and directly compare the RQL approach in viable product designs versus lean staged. The outcome of this work 3 led to the selection of ARC-UL for further investigation. The ARC-UL concept was further refined in the UET program, resulting in technologies that enabled introduction of increasingly lower NOx combustors into the P&W fleet of engines while meeting mandated stringency levels for other pollutants. In addition, the lean staged concept was further investigated during the UET program, where it was determined that the increased complexity in design that results from implementation of lean staging in a production engine was not required in light of the potential of ARC-UL. For the existing TALON family of combustors shown in Figure 2, NOx reduction has been achieved by improving 4 fundamental characteristics of the ARC-UL concept. Figure 3 illustrates these focus areas. They are a uniform rich primary zone, optimized quench mixing, advanced cooling technologies, and reduced combustor residence time. The resulting emissions characteristics for the existing, in-service TALON I and TALON II combustors is compared to legacy Pratt and Whitney designs in Figure 4. The development process for these designs used a range of analysis tools as well as subscale rigs, full annular rigs, and engine tests. The TALON X approach is a significant extension of the TALON family to further reduce NOx by continuing to improve these characteristics. Now let us see the uniform, rich primary zone designed to minimize NOx in the primary zone. It is essential that liquid fuel is vaporized and mixed very quickly so as to create a uniformly mixed rich zone which has excellent stability characteristics and is sufficiently rich to minimize NOx production without producing unacceptable levels of smoke. This uniformly rich front end is achieved by developing fuel injection systems that produce fine, well-distributed sprays that are well matched to the swirler flow field. The TALON X injector is of the high shear style shown in Figure 5. This system creates a fine spray by distributing the fuel over a large diameter filming surface, resulting in a thin film that leads to very small fuel droplets. These small droplets evaporate quickly and track the swirler airflow easily, enabling excellent fuel/air mixing within a short distance of the swirler exit. The spray cone angle and primary zone aerodynamics can be modified by changing the swirl angles of the 2 swirling air passages and the airflow split between them. The TALON X injector and swirler combination was optimized to provide the required level of mixing, and the combustor mechanical design was also improved to control the relative positions of the injector and swirler at operating temperatures and pressures. Next, let us explore the optimized quench mixing. The second focus area for TALON X development was improved quench zone mixing. As shown in Figure 6, it is critical that rapid mixing is achieved to complete combustion of the rich mixture exiting the primary zone with minimum NOx production. TALON X uses an optimized single row of mixing holes developed using a combination of experimental and analytical tools. Jet in cross-flow mixing experiments using carbon dioxide introduced at the fuel injectors and gas sampling instrumentation were used to optimize the hole locations, combustor height, and hole sizes. The resulting hole distribution is a single-row pattern similar to the TALON II, but with circumferential location and size variation optimized for the TALON X application to improve both exit plane mixedness and quench zone mixing. The former is a prime driver for pattern factor reduction, whereas the latter is crucial to NOx reduction. In addition, the data from the experiment was used to develop and validate improved submodels for the All-Star CFD code. This code was then utilized to run a matrix of combustor configurations at appropriate operating conditions to evaluate the performance of the combustor and ensure that it meets the other requirements, such as combustor exit temperature quality. The candidate configurations from the CFD analysis were then tested in a full annular rig to verify and further optimize the design. Next, we can explore the advanced cooling technology. A key supporting technology for quench mixing is combustor liner cooling design, as it determines the total amount of air available for the mixing process. The TALON X combustor utilizes an improved version of the Pratt and Whitney float wall configuration, which provides high levels of cooling efficiency combined with improved materials and thermal barrier coatings. The resulting cooling air budget for TALON X is 20% of combustor exit flow compared to 33% for the base PW4084 combustor. Now let us see the investigations in reduced combustor residence time. The fourth focus area for TALON X was reduced combustor residence time, especially in the quench zone. This is accomplished via optimization of the combustor total volume as well as the distribution of combustor area as a function of length. The reduced cooling air demand discussed above also contributes to a reduction in effective residence time. The resulting residence times for the TALON X prototype and the resulting emissions index of NOx at takeoff power conditions are compared to the existing TALON family in Figure 7. Next, let us overview the results. A prototype TALON X configuration has completed both annular rig and engine evaluation with excellent results. Figure 8 adds the results of the TALON X testing to the NOx versus CO plot of Figure 4, showing a significant improvement in both for incorporation of the combustor into the new Pratt and Whitney geared turbofan engine configuration. Annular rig test results also show that TALON X meets the other key performance parameters noted above. Combustion efficiency data at cruise conditions confirm that there has been no negative impact on this characteristic, and exit temperature data shows that the combustor successfully met this requirement. Engine testing for combustor operability, including starting and lean blowout, also met development requirements. As shown in Figure 9, these results show the capability to achieve approximately 30% of the CAP2 standard, and further improvement is likely as development continues. There are several areas of research that would improve the ability to design and model RQL combustors. New instrumentation capability and experiments to measure reacting flow in a rich primary zone would aid development of modeling tools, as would measurements of reacting jet and cross-flow mixing with a rich incoming mixture. Also, development and validation of soot, NOx, and CO production and consumption models for incorporation into CFD codes would be beneficial. Thank you for listening.